Welcome back. I hope you're enjoying these lessons. Today we're going to learn about effect of electric current on substances. When we were in Form 1, we learned about conductors and non-conductors. I hope you remember those terms. They're going to come in very handy in this topic. But before that, let us describe what an electric current means. An electric current is the flow of electrons and a form of energy. In this chapter, we're going to study different substances and the way they are affected by an electric current. Conductors and non-conductors. From your Form 1, you remember, a conductor is a substance that allows an electric current to pass through it, while a non-conductor is a substance that does not allow an electric current to pass through it. A simple experiment would show us how different substances are affected by an electric current, and we'll note if they are conductors or non-conductors. The setup below shows an apparatus that is used to test for solid substances whether they can conduct electricity or not. The dry cells provide the driving force which makes the electrons to flow in one direction in the circuit. From our structure and bonding, remember that metals contain delocalized electrons that are usually in random order. But when we connect it to an electric current, the flow of the electrons is uniform. Now, from this diagram, the substance being tested is held by crocodile clips steadily, and then we close the circuit. If this substance conducts electricity, the bulb will light, and if it does not conduct electricity, the bulb will not light. Substances that conduct electricity include metals. This is because they have delocalized electrons. We also have nonmetals such as graphite that can conduct electricity. I'm sure you remember this from your structure and bonding topic. Non-conductors are substances such as wood and other non-metals such as gases. Okay, in this setup we can test for gases, but they are non-conductors. Others are something like sulfur. We also have other non-conductors such as salts, crystals. Salts in solid state cannot conduct. We had a setup that was used to determine whether a solid is a conductor of electricity or not. In chemistry, we are also interested to learn if aqueous substances conduct electricity. This setup that we have seen here is used to examine whether a substance can conduct electricity in aqueous state. A substance that conducts electricity in molten or aqueous state is known as an electrolyte. In this case, this substance here, which is an aqueous substance under investigation, is the electrolyte. if it conducts electricity. But if a substance in molten state or aqueous state does not conduct electricity, then it is known as a non-electrolyte. So far so good. I hope we are together. Now in this setup we still have the dry cells and a switch, but we have something special. We have the anode and the cathode, which are known as electrodes. The anode is the electrode that is connected to the positive terminal of the dry cell or the battery, while the cathode is the negative electrode that is connected to the negative terminal of the battery. Now, so what is an electrode? Since it said that an electric current is the flow of electrons, then an electrode is a conductor in which electrons enter or leave the electrolyte. So in this case, once the switch is closed, the electrons will start to flow in one direction and enter the solution, the aqueous substance, which is the solution, through the cathode, and leave the solution through the anode. So the electrons will be flowing in that direction. However, we are not going to study more about aqueous solutions. Our interest will be more on the molten substances, as we are going to see. We described about an electrolyte, that as a substance that conducts electricity either in molten or aqueous state, and we gave an example of a setup that can be used to determine whether a substance in aqueous solution can conduct electricity or not. In this case, molten substances will use a similar setup, but this time will require heat, because most salts and solids require heat to turn into molten substances. And therefore, in this setup, without the heat, the molten substance would freeze back into solid, and therefore we cannot usually use this setup to determine if it conducts electricity, but rather we'll use the first setup we described in the topic. So study this setup carefully and try to show the direction of flow of electrons, and try to describe the cathode and anode as we did last time. Electrolysis. This is the process of decomposing an electrolyte by passing an electric current through it. The setup that we had for molten or aqueous substances is repeated here. Molten and aqueous substances that conduct electricity usually have charges or charged ions. Some of the charged ions are positively charged, while others are negatively charged. And you remember, positively charged ions are known as cations, while negatively charged ions are known as anions. Before we close the circuit, the positive and negative ions are randomly distributed across the electrolyte. If the electrolyte is molten, will require heating. If it is not, then it won't require heating. However, let us assume that this electrolyte is molten, so it will require heat. The electrons in this circuit are randomly arranged, but when we close the circuit, the battery will provide the driving force that will move the electrons in one direction. Now, when the circuit is closed, the dry cells provide the driving force to move the electrons in one direction. When the electrons move in one direction, the electrolyte will have some changes, which we call decomposition of the electrolyte. In this case, the electrons will enter the electrolyte through the cathode and leave the electrolyte through the anode. However, the positively charged ions in the electrolyte will be attracted to the cathode. As you can see, the direction of positively charged ions moves towards the cathode, while the negatively charged ions move towards the anode. Let us make this practical by looking into the electrolysis of molten lead to bromide. Molten lead to bromide is an example of a binary electrolyte. A binary electrolyte means an electrolyte that contains only one type of cation and one type of anion. Solid lead to bromide does not conduct electricity because the ions in solid lead to bromide are fixed and cannot move from one place to another. However, on heating to above 390 degrees Celsius, lead to bromide melts into a molten state. The ions of lead and bromine will become free and move randomly about the electrolyte. In this case, the electrodes that are used are graphite electrodes. Graphite is a suitable substance to use as an electrode because it is inert and does not react with most electrolytes. Additionally, it is a good conductor of electricity and it is relatively cheap compared to other electrodes such as platinum, which is very expensive, although it is the best. On closing the circuit, the bulb will light because molten lead to bromide conducts electricity. Another interesting thing that will happen is that the flow of electrons will move in one direction from the negative terminal of the battery to the towards the positive terminal of the battery or the dry cells. Interestingly, at molecular level, the lead 2 ions will be attracted towards the cathode since they are positively charged, and the bromide ions will be attracted towards the anode since they are negatively charged. From the law of nature, you know that negative charges attract. So negatively charged bromide ions are attracted towards the positively charged positive terminal of the battery, which is connected to the electrolyte by the anode. Once the circuit is closed, interesting observations start to be made. First, it is easy to notice the red-brown fumes at the anode. These are red-brown fumes of bromine vapor. At the cathode, a gray bead of lead metal is formed. From our previous class, we learned that the positively charged lead-2 ions are attracted towards the cathode, and once they get to the cathode, they pick up 2 electrons and form lead metal. In a similar way, bromide ions move towards the anode, and once they get to the anode, they gain an electron to form bromine, and then 2 atoms of bromine combine to form what we call bromine molecule, and that is what we see as bromine vapor. Chemically, these changes can be represented by electrode equations as follows. Two ions of bromine lose 2 electrons to form bromine vapor. Similarly, lead ions gain 2 electrons to form lead metal. This lead metal is the gray bead, while these bromine molecules are the brown vapor. Interestingly, look at the equations carefully and notice that the ions are written in liquid state because it is a molten lead-2 bromide. Similarly, the equation at the anode is written in an interesting way, since bromine ions lose electrons to form bromine molecules, which are bromine vapors. We would have written the equation as follows. However, in chemical equations, we do not usually use the negative sign, and that is why, just like in mathematical equations, we take these 2 electrons to the other side of the equation and they become positive. And that is why our equation at the anode is written in this form. Different binary electrolytes may be used in place of lead-2 bromide. For example, molten lead-2 iodide will form iodine gas or iodine vapors at the anode, that is represented by this equation. These vapors are identified as purple vapors, while at the cathode will form a gray bead of lead metal. Next, molten lead 2 chloride. At the anode, we'll observe a green-yellow gas, that is chlorine gas, while at the anode, we'll observe a brown metal or brown bead, which is copper metal. For aluminium oxide, we'll observe a colorless gas, which is oxygen, at the anode, and a gray bead or gray solid at the cathode. For zinc chloride, we'll observe a green-yellow gas at the anode and a gray bead of zinc metal. That it is used in the extraction of metals such as sodium and aluminium. Aluminium is a very important metal that is extracted using electrolysis. Although electrolysis is an expensive method and other cheaper methods have been devised, however, electrolysis still forms the main method for extraction of aluminium. Manufacture of pure chemicals like hydrogen gas, chlorine gas, and sodium hydroxide solutions. The one is electroplating of metals. When we were in Form 1, we learned that one of the methods of prevention of rusting is electroplating. So electrolysis is used during electroplating of metals to prevent them from rusting and also to improve their appearance. It is also used in the purification of metals such as copper metal and others. So you've seen that electrolysis is the end of the topic. I'm hoping that you have understood everything in this topic. If not, just go back and replay the videos as many times as you wish until you understand. However, don't forget the questions that are going to help you sharpen your skills. Now this time, I'm going to review this chapter in a different way. I'm going to put you to task. Remind yourself the meaning of electrolyte and non-electrolyte, as well as anode and cathode, then binary electrolyte. Then why is graphite a suitable electrode compared to other electrodes such as platinum? Well, that's it for this topic. See you next time.